Hello my friends and business partners from around the world, welcome to my channel. On this video we're gonna see how to use the per phase per unit system of measurement to calculate losses in transmission in an electric power system and the amount of money that could be saved if we constructed the generator close to the load. And to do this I brought to you this exercise. Let me read the problem. Consider the electric power system of the figure. A transmission line from substation number 1 to substation number 2, that's going to be a transmission line, was constructed to connect a 480 volts 5 MVA generator to a 480 volts 4 megawatts load. Considering that the load pays $70 per megawatt hour, calculate letter A, power loss in transmission. Okay, where power is going to be lost? We're gonna lose power in substation number 1, in transformer number 1, there's going to be a Y delta transformer, and we are going to lose power in this transformer. We're going to lose power along the transmission line, and we're going to lose power in transformer number 2. So we're going to calculate all these losses. Letter B, the amount of money that could be saved if we could construct the generator here. If we could construct the generator there, how much money would we save? So this is exactly what we want to calculate, and we are going to begin to do it now. But first of all, what we need to do is to calculate the base values, because we wish to use the per unit system of measurements. And if you have already studied per unit, you're going to remember that we need to establish base values, okay? I'm going to erase it here to get some room for our calculation, okay? And we are going to use the per unit system of measurement. The per unit system of measurement needs bases. We're going to have base values for region 1, which is the region of the generator. We are going to have base values for region 2, which is the region of the line. And we are going to have base values for region 3, which is the region of the load. Okay, remember that the base value of 5 MVA is going to be the base value for all the regions. 1, 2, and 3, we are going to use 5 MVA as the base value of the power. However, the voltage is going to change. The power stays the same as our base value for the power, but the voltage is going to change. For region 1, we're going to use 480 volts. For region 2, we're going to use 14.4 kV as the base value for region 2. And for region 3, 480 volts of voltage. Our voltage, base voltage for region 3 is going to be 480 volts. So, as we can already see, the base values for region 1 are exactly the same as for region 3. Region 1, 480 volts 5 MVA. For region 3, 480 volts 5 MVA. So we don't need to calculate region 3. Region 3 is equal to region 1. So we need to calculate only region 1 and region 2 because they are different. Okay, so the base values for region 1 will be for the power 5 MVA, for the voltage 480 volts. So we want first to calculate the base impedance for region 1, and we use this expression here, which is going to be the line voltage of region 1 squared divided by the power. And I find the value of 0.046 ohms. Okay. Now what we need to do is to calculate the base value for the current, which is going to be equal to SB1 divided by the square root of 3 times VL1. And if I'm not mistaken, the value is 6014.06 amperes. So save these values for me. These are the base values for region 1. Now, what we need to do is to calculate the base values for region 2. And the base values for region 2, we are going to use the voltage of 14.4 kV and the power of 5 MVA. And we do the same that we did for region 1, and we find VL2 squared divided by SB2 to be 41.472 ohms. And the current we find B2 as SB2 divided by the square root of 3 times VL2, the same expressions that we used, and I find a current of 200.47 amperes. Okay, do you guys agree with me? Are you attempting? Are you trying? Please try to calculate and check if these values are correct. Okay, now that we got the base values for region 1, 2, and 3, remember that the base value for region 3 is equal to the base value for region 1. Now that we have the base values, what we need to calculate is the current drawn by the load. So the load is going to require a current from the power system, and this is going to be this. Okay, I'm going to use these expressions here. The complex power is going to be equal to the apparent power in a phase, okay? Remember that the apparent power is the magnitude of the complex power, okay? And another expression that will help us calculate the current is this. Remember that this is the complex conjugate of the current, okay? To calculate the complex power, we multiply square root of 3 times VL times IL, but this is the complex conjugate of the current. Okay, so when we do that, we find a value like this, okay? 4 megawatts is the real power. When we divide this number here, the real power, by the power factor, we get the apparent power. And we need an angle. The angle is going to be the inverse cosine. The inverse cosine of the power factor. And we find a value of 4.348 in the phase 23.07 MVA. Okay? Here it's degrees. Alright. Now we have the complex power required by the load. So the load is going to draw this complex power from the power system. Okay? Now that we have the complex power, we simply divide it by the square root of 3 and by the voltage, and then we have the complex conjugate of the current. Okay, my friends, are you understanding? If you're not understanding, please Leave me a message and I'm going to try to talk to you about your doubt. All right? Okay, so to find the complex conjugate of the current, we simply take this 348, the value of the power that we just calculated, and divide by the square root of 3 and the value of the voltage. And then we find a value of 25,229.83 in the phase 23.07 degrees amperes. But remember, this is the complex conjugate of the current. We don't need the complex conjugate, we need the current itself. So it's going to be the current of the load is going to be equal to 5,229.83 in the phase negative 23.07 degrees amperes. Okay, this is the complex complex conjugate of the current, and this is the actual current of the load. All right, my friends, now that we have calculated it all, we are going to find the per unit value of the current. Okay, why do we need to calculate the per unit value of the current? We need to calculate the per unit value of the current because we have transformers. We have transformers in the system. We have one transformer and we have these two transformers. And what the transformers do? Transformers change power. No, transformers change voltage. 480 to 14.4 kilovolts and 14.4 kilovolts to 480. And when you increase the voltage, what do we do with the current? We decrease the current. So the same current is going to flow through the system. No, it will not. It will not. This current here is not the same as this current here, and is not the same as this current here. How do we calculate then if the currents are different? We need to normalize the current somehow, and this is exactly what the per unit system of measurements do. The per unit system of measurements, this system normalizes, and we are going to have the same current flowing through the three regions of operation of this system. So we are going to normalize it. We are going to use the per unit system, and the current that we find in the per unit system is going to be the same throughout the entire system. All right? Are you understanding? Please leave me a message if you're not understanding. So in per unit, the current of the load is going to be the current that we just found divided by the base value for region 3. Okay? That's why we need base values. When we divide the actual current by the base value, we have the per unit current. And we find a value of this. Okay? Are you guys agreeing with me? Please, if I am making a mistake, correct me and we are going to debate it. Alright? So this is the value of the current in per unit, not in amperes. It is in per unit. And how does this facilitate our calculation? This current here is going to be the same here, here, and here. Although the current in amperes is different here, 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 but when we convert the current to per unit, it's going to be the same. That's why we use per unit when there are transformers in the system. Are you guys understanding? After calculating the value of the current of the system in per unit, we need to convert convert this value here, the impedance of the line, to per unit. And we use the base value for the impedance for region 2. And that's how we do that. The impedance of the line, the impedance of the transmission line in per unit is going to be equal to this impedance here in ohms divided by the base value for region 2. Okay guys, understanding everything? And then when you put this value here and divide by this value here, we find 1.211 in the phase 84.3 degrees in per unit. Okay, why did we calculate this? We're going to use this impedance here and calculate the power lost in transmission. That's why we calculated this value here. Okay. Now that we have everything, we are going to use these values that we calculated to find the losses. Okay, first of all, let's use this impedance here to calculate the losses along the line. It's going to be the power loss in transmission is going to be equal to the value of the resistance of the line, but not in ohms like it is here. It has to be per unit, okay? And I'm going to multiply it by the magnitude of the current in per unit squared. This in per unit, but the current squared. And we find a value of 0.0911 per unit. Okay? But this doesn't tell us much. We are losing in per unit. What we need to do is to convert PU to watts to see how much power we are losing. How do we convert? We take this value multiplied by the base value, okay? This is the base value for the power, and then the power lost in the transmission line is going to be equal to this multiplied by this. I already did the calculus, and then I found 455.78 kilowatts. So this is the amount of power, real power lost along this line here. Now what we need to do is to calculate the other losses. There will be losses in transformer number 1, and this is exactly what we need to find. We are going to use the same expression. We're going to use the same expression to find the losses in transformer number 1. It's going to be P transformer 1 in per unit. It's going to be equal to the resistance of transformer number 1 in per unit. It was already given. It is this value here in per unit multiplied by that current. Okay, take this value here, multiply by the current squared, and then we find this value here in per unit. This is in per unit. To find the value in watts, we need to multiply by the base value for the power. So the power lost, the real power lost in transformer number 1 is going to be 37.6 kilowatts. Okay. Is everybody understanding? Now what we need to do is to use the values for transformer number 2 to find the amount of power lost in transformer number 2. So what we need to do is to simply change here and here, and transformer number 2 here. It's going to be this value here that we're going to use for the resistance, and the current is the same, and then what we find is 0.0151 per unit. And here we multiply this in per unit by this base value, and we find the real power lost in transformer number 1. No, transformer number 1, no. Transformer number 2 is this 75.57 kilowatts. So now that we've calculated the power loss in transformer number 1, the line, and transformer number 2, we simply add these values, okay? And the value that we find is the total power lost in all transmission elements. And the total power lost is going to be 568.95 kilowatts. This is the total power lost along transformer number 1, the transmission line, and transformer number 2. Okay, now that we have this, we can calculate the amount of money that we can save if we could construct the transformer here instead of here. Okay, so we know that the load pays $70 per megawatt hour. Okay, megawatt hour is energy. I pay $70 per megawatt hour. Okay, so, and we know that we lose here 568.95 kilowatts along the transmission elements. What we need to do is to multiply the value that we found for the losses. We lost. We just found this number here. And how do we get from here to here? Simple. This is in hour, megawatt in 1 hour. This is how we measure energy, watt hour. How many hours there is in 1 year? In 1 year, we have 8,760 hours. Okay? Then, if we multiply this 568.95 kilowatts by the amount of hours, 8,760 hours, we get 5,000 approximately, okay? Approximately 5,000 megawatt hour. So this is how much we lose. This is the energy, not the power. This is the energy that we lose in a year. So it is per year. And to finish, okay, the grand finale, to finish, we are going to multiply this by this, okay? If we multiply the amount of money that we could pay or could receive by the energy lost we get the number $350,000. $350,000. So we are losing in transmission $350,000 per year. Okay, my friends, tell me, do you think this is a big number? Do you think this is a big amount of money? For me it is, but maybe for this load here, this is not a big amount of money. And for them, it is better to have the generator here than here. I'm gonna let you decide, okay? $350,000 is a lot of money per year. Maybe, okay, maybe, depending on the generator, we could easily mount it here next to the load and save $350,000 every year. Okay, my friends, this was the video that I wanted to make. I hope you guys enjoyed and learned it using this exercise. Okay? See you then. Goodbye, my friends.